deal with this object, and some friends already knows Silvia and Carlo, for example, we work together and they knows how to handle this kind of structures. Simone knows it, but he tried to forget it. Okay, and I will keep to say, look, I can do the calculation this way. But anyway, I will try also to convince what is the ratio relation between what Simone does and what we are doing. Okay, so okay, I will give you some idea how to perform the calculations. So what are the structures and the way we like to understand these objects. Okay, as I said, I'm not a mathematician, so I will not give you theorems. I will not give you any category interpretation, and certainly I don't speak about Schiffification because I don't even know what does it mean. Okay, so certainly I will not discuss about this point. And of course, any questions is welcome. Please stop in whenever you like it. Okay, so I will try to be very very simple. And first of all, I would like to introduce some very basic concepts, at least to set the stage. Okay, so I will consider a supermanifold M Sm, which has some bosonic dimensions and fermionic dimension. I will denote in this way. This small bracket with n/m means they have n bosonic coordinates and m fermionic coordinates. I will use this dictionary. For me, are synonymous when I speak about bosons. It's a synonymous of even, okay, and it's a synonym of commuting. Okay, so sometimes I use some words which are even, or use bosons, or use commuting variables, or commuting superfields, or even superfields, or bosonic superfields. For me, is always synonymous. And then also are also synonymous fermions, odd, and anti-commuting. Okay, so of course there are several versions of interpreting these things, but I will use in these lectures always as a synonymous words. Okay, so I will denote also by x, a, and theta alpha the coordinates of my manifold. Indeed, actually, what I think about is just about an open patch of my supermanifold, and I will parameterize this open patch by just a superspace. So I will denote a superspace just an open patch of my supermanifold. So I will not talk about let's say global issues about the supermanifold, but just only the flat supermanifold, which I will call it a superspace. Okay, so the index of A goes from 1 to n, and the index alpha goes from 1 to m. For me, for the moment, there are no relations between these two indices. For me, it's just a supermanifold. Of course, if you are interested in some supersymmetric theories, then A would usually represent the vector representation of the Lorentz group, and alpha is just a spinorial representation of the Lorentz group. But for these talks, is not really needed. So I will not talk about A and alpha as indices of a given representations. Okay. And for me, x's are bosonic coordinates, or let's say even coordinates, and thetas are Grassmann real coordinates. Okay, so they are anti-commuting. Again, anti-commuting also means Grassmanns also. Grassmann. Okay. Okay. So then the second quantity, the second ingredient that I would like to talk about is just differentials. So one forms differentials. So dxa and d theta alpha. Okay, so dxa and d theta alpha are the fundamental one forms which are usually needed to build the cotangent bundle. Okay, or the space of forms. Okay, and for me, dx's are odd coordinates. Okay, and d theta are even. Okay, in which sense? Well, in the following sense. Okay. I will always talk about with respect to the wedge product. Okay, so this means dxa wedge dxb is equal to minus dxb wedge dxa. Then dxa wedge d theta alpha is equal to d theta alpha wedge dxa. And then finally, d theta alpha wedge d theta beta is equal to d theta beta wedge d theta alpha. Okay, so the dx are anti-commuting variables and the d theta are commuting variables. Also, actually, I also works in this way. So I have a theta alpha dxa, and I interchange the positions. I get a minus sign dxa d theta alpha. So what is anti-commuting? Anti-commutes with all the anti-commuting variables, and is commuting with the bosonic variables. There are several ways to do this. I mean, this is one assignment of parity. Okay, there is another assignment of parity which works also fine. However, I will not talk about the other possibility. I will stick to this. Okay, in particular, the differential d. Okay, is a node operation, so it's not a derivation or an anti-derivation. Okay, in this language. So okay, so then once we have these ingredients, so we can start build forms. Okay, first I would like to talk about superforms. Okay, the superforms are usually the type of forms which is just the naive generalization of differential forms in conventional geometry. Okay, and so then I will denote them in this way: P/0. Okay, the second index here appearing in this formula, it stands for another gradings. I will talk about these other gradings in just a second. Okay, however, I will tell you that this grading, we call it pictures. Okay, so this object P/Q means is a space of P forms at 0 pictures. Okay, the superforms are the 0 picture forms in this language. Okay, so the superforms are essentially what you expect to call a differential forms in supergeometry. Namely, if you consider, for example, a P form in this language, what is well, I can do the following. I can write down this in some component functions, A1, AR, and alpha R plus 1 dot alpha S alpha P. And then I have a dxa1 wedge dxa wedge. I will go on the other line, d theta alpha R plus 1 wedge d theta alpha P. Okay, so I just expanded locally my P forms in terms of let's say the basic generator of this fiber. Okay, the component fields here you see are, of course, they have some indices because there are several components, and in particular, if you look at the indices, the first indices are antisymmetric, and the second set of indices, however, is symmetric. Okay, so I will denote by in this way a.
Antonio, yes. I cannot read the indices, so
okay.
A goes from A1 to A what is very small.
Oh yeah, so let me increase the size. Sorry. Okay.
Yeah, just a bit. Okay.
Gosh. It just jump. Okay.
Yeah, no, but what is P? I mean, P is
just the form number. The form number.
But, so the indices go from 1 to R, and then from number. R plus 1 to
the index. Okay, we'll write down bigger here. 1 up to R. Okay.
Yes.
And then alpha R plus 1 alpha P. Okay. So the total number of indices is P, and of course you can separate. You can divide the interval between 1 and P into A indices, namely the indices related to the bosonic coordinates, and the alpha indices, which are the indices related to the fermionic coordinates. Of course, the first set, namely A1 to IR, are anti-symmetric. Okay, if I exchange two indices, I get the minus sign. The other set is symmetric. I will use this common notation in physics to denote by a square bracket the anti-symmetric set of indices and the round bracket to denote the symmetric set of indices.
Yeah, one thing I don't understand is that omega P0, is it an even object, an odd object, or you cannot establish the parity?
Okay, good. Okay, essentially all these components are superfields. Okay,
yes.
So this means that they have an expansion. I can decide to set a parity, a given parity. For example, I can decide that this superfield is an even superfield. So this means that if I expand in component, okay, all the components will respect the parity accordingly. Of course, I can also define anti-commuting superfields, so odd superfields, and therefore, even in this case, those components must respect the parity, the total parity. However, it doesn't need that. I mean, you can choose a superfield which doesn't have a definite parity, okay? And this means the component could be even or odd. Or, for example, you can take all odd component or all even component, and therefore the parity jump from one component to the others, okay? This is not really needed at this point. Of course, in physics, okay, when you talk about the Lagrangian, for example, which is a superfield, for example, of course, the Lagrangian must be a bosonic quantity, and therefore each component must have different parities, okay? However, I'm not forced at this level to decide what is the total parity of a superfield. Okay?
Yes, yes.
Okay, very good. Good. So all these components of the form indeed are superfields, okay? And as in the usual case, I can act with the differential D, and differential D map P with 0 into omega P plus 1 dash slash 0, okay? So the differential D increases the form number, okay? And how it works? Well, as usual, if you act on the D of omega, which is a P and 0, and then you calculate them in the usual way. So you have dx m and then derivative of this of the form omega, and of course all these indices. So let me use just a very compact notation in this way, and alpha to denote all these and all the thetas, okay? Now, of course, and then also the other terms, d theta beta, d beta omega a and alpha, okay, in d axis and d thetas, okay? Of course, actually, when I write out these things, I first take the derivative of the function which is in front of my differential forms, and I have to anti-symmetrize with respect to all the other indices for the first line, and I have to symmetrize with respect to the thetas. So the total result will certainly have a p plus 1 forms in this language. So the differential in this case works exactly as in the usual case. However, the complex of forms, okay, which I denote in this way, 0, 0, then the differential maps into 0, 1, 1, 0, sorry, the differential D map into 2, 0, and so on, okay? Of course, this complex, okay, has no upper bound, so no upper bound. Since I can go upper bound, since I can go over with the number of d thetas, so there is no upper bound in the form degree. I can have a form with any number I like, okay? So there is no upper bound, and so there is no top form in this complex. So there is nothing which transform exactly as a top form in this framework. Of course, with respect to axis, certainly I will have some determinant coming up from a given transformations, but from the d theta part, it doesn't combine in a very geometrical way. So it's completely arbitrary, these things. Now, of course, you can do two things. Okay, you can stick to the polynomial representations In some cases, in some papers, in some work, actually, some people also try to say, well, it could be an analytic expansion of the data, which corresponds to the series expansion of this, but it could be something more like analytic functions. However, I will not go into these complicacies in this case. Okay, just only I will stick to this just to polynomial representation of this form.
No, but
Okay.
Antonio, don't understand what you mean with polynomial representation. I mean, the omega, the fields could be anything, right? They don't have to be polynomials, can be anything.
No, of course, polynomial in d axis and d thetas.
Ah, okay.
In principle, if you see d thetas as some commuting variables, in principle, nobody prevents you to consider analytic function of the thetas. Of course, okay, it's tricky and it is well not very well settled, but in some sense you can do it. Okay, for example, you can write down a Gaussian of e to the minus d theta square. Why not? Well, of course, you can interpret this function in terms of series. So it doesn't make any difference in this case. However, you have to be careful if you encounter some poles on d theta. So then you have to understand what are these kind of poles. So d thetas are not numbers, but I will treat them as just commuting variables. Okay. Good. So the next set of objects that I will introduce now are the integral forms. Integral forms. So, okay, integral forms are very well suited to build a geometric integration theory for supermanifold. In particular, if you want to integrate it, if you want actually to integrate a differential form, as in the conventional geometry, you have to say how you integrate it on variables axis and also on the axis. So, namely, how you translate from a top form into the function that can be integrated a la Lebesgue or a Riemann integral. Okay. In the case of d thetas, so if I want to integrate on such variables, please notice the difference. When I talk about integrating on a given variable, okay, means that I will consider d theta as the variable on which I integrated. For example, if I have a superfield phi of x and theta, certainly I can integrate these superfields in my supermanifold phi of x and theta, okay, as just a superfield, which means an integration on x variables and theta variables. Just only to be kind to my let's say my audience, I will just put this symbol dx and d thetas here, okay. But please note that for me it's just a symbol, doesn't make any geometric interpretation. However, if you read in the paper by Witten, he gives a geometric interpretation of this symbol. Well, just for me, just only symbol to just to remind us what are the variables on which I integrate. Okay, and this integration is what? Well, this integration is just the Riemann-Lebesgue integral on x variables and the Berezin integral on theta variables. Okay, which means essentially which means a set of derivative, let's say alpha 1 up to alpha m of the function phi computed for theta is equal to 0. This means the Berezin integral, namely a set of derivative, and on top of this is just the bosonic integral. Let me call it the axis here. Okay, this is just what is known as the superspace integral. And this object here, appearing here, this object here, let me call it a measure here, is what actually Simone was discussing in this lecture. So this is just the Simone measure discussed in his lecture. Measure, okay, discussed in this lecture. In his lecture, namely, this is just the superspace integral. It's not an integral for a differential form or for an integral form. It's just the integral of a superfields. So,
but Antonio, here you are making example of R and M, right?
Yeah, R and M, sure.
R and M, okay.
Sure. The symbol d axis stands for what actually in the first set of calculus lecture, usually people denote like d and x. Okay, just a symbol. Okay, I'm not pretending any transformation property of this object for the moment. Okay.
What are the capital D's in front of the field? What's that?
The capital D's. Okay. So, yeah. Okay. The capital D's are the differential with respect to the thetas. Okay. Usually I use the notation d alpha, okay, because I denote this as the super derivative. Okay. The difference is very simple. Let me just put a note here. Okay. If you work on this particular superspace, okay, and then you have dxa and d theta alpha. You can also have the vector fields dA and the vector fields d alpha here. Okay. Now, in terms of these vector fields, you can build other two sets of vector fields, dA and another vector fields, which is the following: Q alpha is equal to d alpha plus gamma A d theta alpha dA. Okay. Now here I introduce this object, which are the Dirac matrices. Okay, which actually converts the spinorial indices into a vector indices in this way. So of course the Dirac matrix depends crucially on the dimensions. And there are on the dimension and which representation of spinors you are talking about. Okay, for the moment it's not needed to specify this point here, but the crucial point is that if you calculate the anti-commutators of these vector fields, the anti-commutator, not the commutator, because those are odd vector fields, it gives just A alpha beta dA. And this is just a representation, actually factor 2, it is a representation of a supersymmetry, okay? So these charges are known as a supercharge, are odd vector fields, and they implemented the supersymmetry in this framework. There is another set of vector fields, which are usually called superderivative, which the difference between them is just a minus sign between them, okay? And this set of vector fields anti-commute with the first set, okay? And it's also a representation of supersymmetry with just one big difference, which is a minus sign in front here, okay, alpha, beta, and dA. So it's again a representation. Please notice that these minus signs, okay, and these two sets of vector fields anti-commuted by themselves. Now, if you have these vector fields, okay, namely dA and d alpha, okay, correspondingly, you have one forms, okay, one forms, which are usually denoted VA and psi alpha, which actually are written in this way. VA is a dxa plus a theta gamma A d theta, and psi alpha is a d theta, okay? And those one forms are actually supersymmetric invariant. So they sometimes using the d vector field or the q vector field, and correspondingly using the v one forms and the psi one forms allows you to keep the supersymmetry manifest to each steps of your calculation. However, since we are at the moment not really interested in supersymmetry, I will not discuss further this point. So to get back to the John questions, actually in terms of these D's, I just can use only the differential with respect to the odd coordinates. It doesn't make any difference at this level. Okay.
No, so I have a question. So the coordinates, also Silvia was speaking about these coordinates, right? So yes. The vector fields D are a frame corresponding to these coordinates, right? Correctly,
exactly. In fact, these two fields are actually known as the super field binds or super frames. Correctly, exactly. Actually, you see, Rita, this notation VA psi alpha. Can you see my page? Okay.
Yes.
Okay. This indeed is just you go from a flat dxa d theta alpha into this slightly curved manifold, which is not really a curved manifold, but actually this particular set of superforms manifestly keep the supersymmetry, okay? And indeed, going from this set of forms to these forms, there is a matrix, which is the super field bind matrix, okay? Which has the following form. If you like, I can write down for you. the frame, okay, actually you can write down as a matrix, which has an index A, where the index A goes from A and alpha, and the big index down, which is just an index like goes M and mu. And this is just a matrix. In this particular case, the matrix of these types is the delta, the Kronecker delta M and A, gamma A theta with the index mu, 0, and delta mu alpha. Okay, so in this particular case, Rita, that's really the frame. Okay.
No, it's very clear because this is the Jacobian of the transformation, and the columns, so to speak, or the rows as you please, form the vector fields, right? But why would you go to this curved, which is only super curved, because when you...
Well, it's not really curved.
Yeah, it's not...
Well, using this frame, what happened is that the superspace get a torsion, okay? It's not curved, but you get a torsion, okay? Indeed, actually, if you calculate, for example, the differential of VA, okay, this is just a Maurer-Cartan equations, and usually when you calculate the differential of the frame, also, okay, to be precise, you also, if you have a curved manifold, you have a spin connection on the manifold, okay? But in this case, I didn't switch on any spin connections, but it turns out that anyway, this gives these equations, which means that you get a torsion for this super manifold, okay? So, well, let's say the only component of the torsion is just a constant component of the torsion, that's it.
So perhaps we could say that our space is not abelian, it's like a two-step nilpotent Lie algebra somehow.
Yeah, sure, exactly. Well, it is not curved, it has a torsion, and indeed, actually, it is non-abelian in this sense. Okay, you're right.
Okay, no, thank you.
And actually, the structure constant of this non-abelian step are indeed the Dirac matrices.
Yes. No,
which are the intertwiner between spinorial representation and vector representation. Okay. Let me go with the integral forms. Okay. Now, actually, what I want to do now is to try to define a way to compute integrals not for superfields but for forms. Okay. So this means I have to invent a way. Okay. First of all, my integral, I will promote the integral in this way. So I use now the Simone notations for, okay, first I will write down then, and then I will explain this notation. Okay, well, as Simone explained, this object, this object here, okay, is just the cotangent bundle of my supermanifold, okay? However, I put the pi in front, okay, and actually, this is just the only time that I will speak about a functor, which I mean I learned from Simone that is called a parity functor, which means essentially that I'm not talking really about a cotangent bundle, but what I'm really talking about is the supermanifold, which is the changed parity cotangent bundle. And this object has the following coordinate: xa, theta alpha, dxa, and d theta alpha. And for them, I use the fact that the x and d theta are bosonic, okay, and theta and dx's are fermionic coordinates, okay. So if I stick to my notation again, I have dx, d theta, and then I have d of dx's and d of d theta, just only to list my variables, okay. And then here I have to put some integral forms. Okay, let me first write down this in this way, and then I will discuss about this. What is this object? Okay. Now, the measure that I put here, let's say this is a symbol. Okay, this symbol that I put here. Okay, just only it's neat. Well, I will do it just only to keep track of what are the name of the variables that I integrated over. Okay, so the first two are integrated according to the previous slides. And then I have to explain you how to integrate it on the next slide, in next two set of variables. For what concern the axis, okay, those are anti-commuting variables. So for them, I use again the Berezin integral, okay? So this means what? Well, means that if I have a form, okay, if I have a form, I will extract the top part of this form. Okay, so I will have to select the top part of this form. Okay, what about the d thetas? Well, d thetas, if I insist to consider them as just commuting variables, okay, I have no way. I mean, either I invent a regularization or a way to regularize my integral, or I have to put just a convergence factor. Okay, but let's say the easiest way, at least I think also not only the easiest way, but one of the most reasonable way is this, well, to use the atomic measure. Okay, the atomic measure means the following. So I insist that my top form here will be proportional to what? To the axis. In this way, I will have n of them, and then I put just the atomic measure, namely d theta 1 wedge d theta m. Okay, so I put really a Dirac delta functions which project me into d theta is equal to 0. Okay, so d theta are not numbers. Okay, the most reasonable value that they can have is just d theta is equal to 0. Okay, so therefore, let's say this is, let's say, the obvious choice, just only the atomic measure which you put d theta is equal to 0. Okay, that's reasonable. It is not the only one. You can do something different. Okay, if you like, I can tell you what you can do. But in principle, any convergence factor, for example, before I was talking about, what about if I put like something like e to the minus d theta square, for example. Okay, so a Gaussian factors, which allows me to do really the integration. Yeah, you can do it. Okay, actually, you can use just a symbolic integrations. Well, you can use a kind of a Gaussian integral also for this object. However, d thetas are not really numbers, so it doesn't make any sense what is the d theta square or e to the minus d theta square. Of course, you can get around about this point, but okay, in my opinion, this is still a little bit problematic how to interpret this object. However, if you do it in this way, just only adding just this delta of this, then you are safe. You can do the integral. Integrating on d thetas is just the usual integration on the Dirac delta function, namely delta of d theta integrated on d of d theta. This give you on a function of d thetas, give you just the function computed at 0. Okay, this is just my definition of these Dirac delta functions. Okay, I will not use, I mean, Simone in his talks actually point out that he doesn't want to use analytical property. I also don't use analytical properties, not completely. Sometimes I use analytical properties, okay? But the crucial ingredient that we need for manipulating this object are the following. So if
I cannot read. So you wrote the integral of delta d theta,
yeah,
right?
Sorry. Okay, let me write.
I'm sorry. It is, yeah. Thank you, because I cannot see.
Delta of d theta.
Okay, thank you.
Okay. Now, what are the properties? Okay, the properties are the following. Okay, so if I take a delta of d theta, okay, and I multiply it by d theta.
So can I ask you? In this case, the integral is over a point, right?
Well, the integral localized on a point. Okay, it's
But there you wrote an integral. What is the supermanifold of that integral?
I mean, just the usual superspace. I mean, flat superspace.
Yeah, you're integrating.
But I think it's just, I think it's R01.
Yeah, exactly.
With coordinate d
It's
theta.
over a point.
Yeah, exactly.
Yeah, geometrically.
Well, actually, this particular integral.
Yes.
Yeah.
No, this is not true. Okay, this is just the integral on a fiber. It's not an integral on. Okay, it's just the fiber d thetas. It's not on a point at this point. At the moment.
So
No, but Antonio, you are integrating over a supermanifold. What?
Oh, okay. Wait, Rita.
No.
Okay. Let me go back. Okay, this is the integral that I want to make sense is this one. Okay, this is the integral I want to make sense. Okay, I'm integrating on the Pareto change cotangent bundle of my supermanifold. Okay, that is the integral I want to make a sense. Now here, the integral that I wrote down here is just only to tell you what are the integration on d thetas. Okay,
no, I am happy, but what is you're integrating upon? That's all.
Sorry, please repeat.
When you write an integral, it's like on something, and I don't know what that is.
So yeah,
Are you talking about
fiber?
Sorry, are you talking about this integral or about this integral?
That one, that one.
This one is just the integral on a fiber.
Yeah, but what is the fiber?
The fiber is the fiber of d thetas.
On an arbitrary point is in Rn. The
Yeah,
fiber of an arbitrary point.
Yeah, well,
yeah, it's like the fiber integral that stays into the integral, well, let's say the total integral over the parity shift tangent bundle of R01.
I'm
So
happy.
the fiber.
no, wait a moment. I'm not integrating on the cotangent bundle. This is just the integral on the fiber.
It's just the fiber part.
Okay, good. Okay, exactly what
just the fiber
Paolo
part.
was saying is just the integral fiber. But please notice that I'm not telling you that the d theta are numbers. So I'm not integrated on R. Okay, I'm integrated in something which is d thetas, which are not numbers. And I only just said the only value that the d theta can get is just 0. Okay, so I integrated on one point, so it is a localization on one point on d thetas.
No, but Simone said something, and can you repeat? So you are integrating over what?
So if you think about a supermanifold which has only one single odd variable, so say, for example, R0/1, and you want to integrate over this supermanifold, as Antonio explained, you basically lift this supermanifold to something which is canonically related to this supermanifold, which is the parity shift tangent bundle, okay? And then your integral becomes an integral which is both on the manifold and on the fibers. So on the fibers, because you know the point here is that you really want to integrate like forms in some sense. So the fibers is something like R, even R, because d theta is actually even, okay? So this integral over here take care of the part of the integral along the fiber. So along the fiber, which basically describe your d thetas, okay?
Is it clear, Rita?
And you don't have, actually, in this case, you don't happen to have anything else because you're moving above a point, R01.
So here you just have the coordinate theta, right?
Exactly.
Yeah, but please notice that this integral is not an integral over theta.
No,
Exactly.
no. But can you go back? Can you?
Sure.
Yeah. So, yeah, I am confused because I would like to have in the second integral also d theta.
Yeah, it's
not there.
That part,
No,
exactly.
no,
So that part is on the base.
Yeah.
Say.
Okay. Let the point. Okay. So what Simone was talking about is something, and also John was this kind of a superspace. Good. Okay. Now, if you want to integrate on this superspace, okay, now you integrate on this object T, parity changed T star of R01. Okay. And now this has a two integration variable, d thetas and d of d thetas.
Yes, I'm happy. Yes.
Okay, and then what actually you can integrate? You can integrate a function of thetas and a function of d thetas. Okay.
Yes.
Okay, good. This function of d thetas and the d thetas, I will use a following object, a function of thetas and delta of d thetas. Okay. Is a given object, okay, which has the following properties, that it localizes where d theta is equal to 0.
So your f theta here is 1, right?
So the number
the
of
big F in your example is 1. Is just a number.
Where?
Your integral, the big F is 1, is not there. So it's like is 1.
No, okay, but no, let me do the calculation, okay? If
Yes.
you want to do the calculation, okay, you have two set of variables. You have the variable theta and the variable d thetas, okay? Then you have f of theta and then f of d thetas, okay?
Yes.
Good, okay. If you like, I can also put this symbol, okay?
Yes.
Now, what happened? If I want to integrate on the theta, then I use the Beretsin integral, okay? But I want to also to integrate on d thetas, okay? The final answer is that d theta is set to 0, okay? And the theta is, you just have the derivative with respect to the theta of f of theta computed at the theta equal to 0. That is the final answer of this integral.
Yeah, I have a small question.
Yes.
That when you write a little f theta d theta, right?
Yes.
You're writing a big F of theta and delta d theta. Why don't you have a function of d theta?
Yes, I can have, okay, you're right. I can have a generic functions, okay?
Okay.
However, if I want to integrate a generic function, and if I integrate a generic function, I have to say something about how can integrate on d thetas, okay? But the d thetas are not numbers, okay? D theta are what, who knows what are these objects, okay? Okay, therefore, the only, at least one of the most reasonable way to integrate on d theta is just using the atomic measure, namely d theta is equal to 0. And this d theta equal to 0, it is actually achieved by choosing a specific set of functions, f theta d theta, which are proportional to delta functions. Okay. And those are the integral forms. So those functions, those generalized functions on theta and d thetas, which are proportional to delta or d theta, are integral forms. Did I convince you?
Yes, my question was a formal question because the integral that you wrote as your first line was not of the same type of the one you wanted to define. So that what.
Well, okay, okay. In some sense, these lines here that I wrote here, okay, it was just a way to explain you actually how you integrate on d thetas. Okay, the type of integral that I want to discuss are those type of integral. Okay?
Yes, yes.
Okay, okay. Once we understand that, okay, so my integral form n and m, okay, now finally I can represent those objects in the following way. So locally, okay, locally I have a function a1, an, which are antisymmetric indices here. I have a dx a1 wedge dx an, okay, and then here I have a set of delta function, delta of d theta alpha 1 wedge delta of d theta alpha m. I will still keep the notation wedge, okay, for the following reason. This delta of d thetas are distribution, okay, but to be more precise, those are the RAM current, okay, and for them I will use the following property: d theta alpha wedge delta of d theta beta is equal to minus of delta d theta beta wedge delta of d theta alpha. Okay, this is very important because actually, so this delta of d theta, they looks like anti-commuting variables and not commuting ones. Okay, so, and this is a crucial. Okay, this is crucial because now you immediately see that the number of delta function that I can put, okay, is just limited by the number of fermionic directions. Okay, so therefore I can only have m possible delta function along the different directions. This actually eliminates two problems. One problem that eliminates is the fact that now we have a top form. Okay, first we have a top, let's say, an upper bound first. And the second problem that it eliminates is the fact that I can never write down something delta of d theta 1 wedge delta of d theta 1. I never write down such a thing, so because in this way it is automatically 0. You know that this is in a distributional language, the product of two delta function in the same point, it's very problematic. You have to regularize, you have to choose a regularization in a point. And in this way, I choose the regularization in such a way that if I multiply delta d theta with delta d theta, then automatically gets 0. Okay. Those are.
I am bothered by the presence of a Roman index.
A Roman?
Yeah, you wrote d theta alpha and then d theta a.
No,
Beta alpha.
A beta. This one.
Thank you.
Okay. Okay. So then, okay. So this eliminates the two problems. Okay. I'm not yet done. Okay. So this is what we know as a n/m integral form. And the second index here, it is, as I said before, is just the picture number. And actually the picture, it counts the number of delta functions, okay? So in this case, we have all possible delta function. This means m delta function. So the picture is the maximal one. So the super forms are those with 0 pictures. Integral form are those which have maximal pictures, okay? Good. Now, actually, you can do two things, okay? First of all, I would like to tell you how the differential D works on the space, okay? How the differential D works in the space? Well, the differential D works again in this space in the following way. n/m goes into n+1/m. So again, it increases the, okay, let me use it here instead of n. Let me be more specific, p/m and p+1/m. So the differential D, it increases again the form number. Okay, let me first show you how it works for this particular form. If I act on D of omega n/m, okay, then I have the following things. I have dxb, derivative with respect to b of omega. I use again the compact notation, dx wedge dx, okay, times the delta function, d. I will use again also a very compact notation for this, okay. Let me use this compact notation, which is delta d theta wedge delta of d theta, okay. And we have m of them, and here the n of them, okay. Now, and then there is another line. As I said before, I have another line, which is derivative omega a, and then I have dx's and delta of d thetas. Okay? This is my two lines, okay, of my differential acting on this form. Okay? Now notice the following. You see, it happens the following. Here there is a differential d, this one, okay, and then here there is a set of m differentials, okay. Then automatically, if I want to symmetrize on n+1, this gives you 0, okay. So then automatically these terms is 0, okay. Now let's look at the second line. Here, Lucy, here there is the d thetas coming from the differentials, and this object hits the product of this, you see. But then you see immediately the following, that if you have a d theta alpha, which hits a Dirac delta function, the distribution rules tells me that this must be is equal to 0. Okay, this is the usual distribution rules, that delta d theta, it projects into the 0 the functions which is in front of it. Okay, of the same.
I don't understand. Why is the first term going to 0? I don't get it. Why? Why is it going to 0?
Oh, okay. Yes, because actually you have n differential, dx1, dxn.
Oh, I see. You have the maximum number. That's
exactly
what you say.
Exactly.
I see.
Sure.
Okay.
So then you multiply it by an additional one. Of course, there is a wedge product.
Yes, yes.
Right? Then automatically get 0. Okay. So this form n+m is actually, it plays the role of the top form. Please notice, I just only to make a remark, okay? So I use the differential D in a very sportive way, okay? Namely, I just use the D as it is, okay? Just doing this calculation, okay? I will come to, okay, I have to tell you one thing, which is the following, okay? if I want to really to use the differential in this very sportive way, okay, let me tell you the following. What is this object? What is the differential of delta? Okay. Now, if you calculate the differential of delta, I just use the following rule. Okay. First, I will take the derivative of the delta function with respect to its argument. Okay. And then I calculate the differential. Oh, please notice that when I go over delta, I get a minus sign because the delta essentially it is an anti-commuting quantities. Okay. So therefore, if I go over with the differential, I get a minus sign. And then this acts on d alpha. Okay. Now, if actually, since this is just a one form, then this automatically gives 0. Okay. So when I act with the differential on the delta of d theta, then automatically I get 0. This is the first things. Okay. The second thing is
I don't understand why d theta alpha delta d theta alpha is 0. I mean, it's probably obvious. I don't see it though.
What, you don't understand this?
No, the previous one.
Which one? This one?
Yeah.
Well, okay. What is the definition of direct delta function? A definition of direct delta function is the following: the integral of any function. Sorry, what? Let me use another notation because otherwise it's confusing. D thetas of delta of d thetas. Okay, this integrated on d of d theta. That gives me the function computed 0. Okay.
Yes.
This is just the definition.
Yes.
Okay? I use this definition. So therefore, if my function d theta is just d thetas, okay, then this means that the computed 0 is just 0. Okay. So let's say let me remind you what is the Schwarz distribution delta of x. Okay.
Okay.
Okay. Now you know that there is this rule. Okay, which means is equal to 0, namely the integral of a function of x of delta of x integrated on the axis on the line. This gives me just a function computed 0. Okay, that's the usual where f is a test function. Let's say a Schwarz test function on the line. Okay, and the delta is belonging to the dual of this space, which is just the distributions on the space, where f are the usual Gaussian type of test function. If you like, these are temperate distributions.
Okay.
Okay, so I use this rule. Okay. Good. So this allows me to introduce another object. Okay. So if I'm allowed to use if I'm allowed to use direct delta functions of d thetas, okay, certainly I'm allowed to use any derivative of those. Okay, any derivative of those are well-defined objects. Okay, because the derivative of the direct delta function are defined in terms of the test function. Every time you have the derivative of delta function by integration by parts, you can replace the function with the derivative of the functions, essentially. Okay, so I'm certainly allowed to use any derivative of delta functions. Okay, a second set of rules, I don't use like non-compact distribution. Okay, something like this, I can define something like this, but I'm not going to use this object. So I don't use any non-compact distribution with the non-compact support. I just only distribution with compact support, in particular delta functions, essentially, or derivative of delta functions. Okay, just only to set the stage. So therefore, if I'm allowed to use derivative of delta functions, okay, then I have two following things. If I have a form which is now as a p/m form, so not the maximal form, okay, but just any p which belongs to, well, okay, first of all, let me say, let's say p, it is minus or equal to n. Okay, I have to establish what is the lower bound. Okay, suppose that the p is less or equal to n, where n, I remember n, I recall you that is just the bosonic dimension of the supermanifold n/m. Okay, suppose that I consider an integral form which has a form degree which is not the maximal one. Okay, so how can I write down this object? Well, I can write it in the following way. Okay, I have certainly some component, some function here. Okay, then I can have several things. First of all, I can have dx, how many times? P times, okay? And then I have all the possible delta functions, d theta 1 times delta d theta, all the possible theta functions, okay? Certainly, this is a P form and has a picture number m. Please notice that the delta of d theta carries no form degree, but just only a picture degree, okay? So you see that the form number is just carried by the d-axis, and the picture number is carried by delta of d thetas, okay? However, this is not the only case. Why? Well, the reason is the following. Suppose that I consider a derivative of d thetas.
No, but Antonio, this is not what you told us before. For you, omega p0 was comprehending also the d thetas, right?
Yeah, sure. The p0 comprehends the d theta. Here, certainly, I can put also d thetas here, okay? Suppose that I put some d thetas here, okay? Suppose I can do it, okay? However, you see that you have all the possible delta function along d thetas. And then using again the rules, the d theta, delta of d theta is equal to 0, then all these terms drops out. So there is no way to put a d theta. Okay, so this object, certainly I can put it, but it's a completely...
I see. So I see, okay. Thank you.
Okay, let's see.
What happens when you have a d theta alpha multiplying a delta d theta beta? Is that...
like a d theta alpha?
Yes, times delta of d theta beta.
Okay, of course, this is not 0. Yes, yeah, right. This is not 0.
Does it commute or anti-commute?
Of course, it commutes because this object commutes, is a commuting object. This is an anti-commuting object. So they do commute.
Okay, sure.
Okay, but this is very important. In this particular framework, we never get these terms. However, I will show you another sector where indeed this is very important. Okay.
No, okay, because you chose the maximum fermionic, that's why, right?
Exactly. The maximum fermionic dimensions in this language is called the maximal pictures. And since I am talking about the maximal picture now, there is no way to put a detail. However, okay, let me first of all tell you what is the derivative of this. Well, you see, d theta is in my language is a one form, okay? So a derivative of this type is essentially in the, let's say, in the conventional geometric language, a derivative with respect to one form, okay? It is what is known an interior differential, okay? An interior differential is also known as a contraction operator, okay? So this means is a contraction along these vector fields of delta of d theta. Okay, just only to tell you, I mean, just only to respect the correct geometrical nomenclature, a derivative with respect to a one form, it is expressed by, say, if you look in the book by Kobayashi and Uemitsu, by the contraction along the corresponding vector field. Okay, namely, corresponding vector field means that if I do a contraction with respect to theta of d theta beta, this gives me a delta alpha beta. Okay. That's what I mean by a corresponding vector field, which is the dual to the d theta. Okay, so this is the usual. Okay, this formula actually you cannot understand this formula as the d of the d theta alpha times theta beta, and this gives you exactly delta alpha beta. Okay, I hope that it is clear this formula. This is formula number 0 in the Kobayashi and Uemitsu.
But L is what?
This little is a iota, is just a contraction along the vector field. Okay. Thank you, Marianne. Okay. Yeah, I will use these notations. Okay. In the slides by Simone, he was talking about polyvectors. Okay, and indeed from the shift theory point of view, since in this case you are interested just only on the transformation properties, a vector fields or a contraction along the vector fields transform exactly in the same way. And therefore, in this case, he was using polyvectors, and those polyvectors discussed by Simone are translated in this handy formalism as a contraction along one force. Okay.
So I sort of lost when you were taking the delta prime, right?
Mm-hmm.
You mentioned it before the delta prime.
Yes, I mentioned before, yes, delta prime, yeah.
I cannot see it in my notes. When did we? So how can, yeah, right. You mentioned it.
Well, I don't think I actually.
Oh, you never mentioned it.
No, I never mentioned.
No, you mentioned it there.
Oh, you did. You did.
You did. Go one page up.
Ah, yes, exactly.
Yeah.
Okay, yes. Okay.
All right.
So
I am very confused to reconcile what you did.
Go up. It's even easily mentioned before.
okay. So essentially, what is a derivative of delta function? Okay. Essentially, again, if I take a let's say a test function. Okay. Suppose that I have a test function of d theta, and then I apply the derivative of delta function d theta. What is the, and then integrated on the d theta. Okay. That gives me what? Well, it gives me minus to the n, okay, of derivative, now n derivative respect to d theta, okay, n derivative respect to d theta of my function d theta computed at the d theta is equal to 0. Okay, that's the usual definition, integration by parts. Okay, every time you have a derivative of delta functions acting on a test functions, you get just integration by parts. Okay, and this -1 to the n is just the fact that you are integrating by parts.
So on this point, can you show me how this translates in the contraction operator?
Yeah, that I don't get. Yes.
Oh yes. Okay. Yes. Yeah, sure. I can do that. Okay. Certainly. So the contraction operator is indeed a derivation. Okay, because it is really a derivation. Yes. There are four. Okay. Yes. So this means that indeed, if you have a g of d thetas, okay, and then I have a contraction operator along alpha of delta of d thetas, okay, so then you can rewrite this as just alpha of g of d thetas, okay, a delta of d theta minus e alpha of g d thetas. Sorry, I use the alpha, just a shorthand notation for just only to say I have derivative with respect to the vector fields, okay? So, and then I get the d thetas and delta of d thetas, okay? So this actually, okay, so this object here, it's a 0 because of the stock theorems again, okay, essentially, okay? And this part here is just the integration by part. So also for this specific integrals, okay, which integrate on d theta works Stokes theorems, and the derivative here is just the contraction operator. So there is a beautiful way to see this, okay, by define this integral in terms of some differential operators. Yeah.
Okay, I understand. But this works only if you have d thetas. In the classical case, there's no such operation. I mean, it's just the usual partial derivative with respect to the coordinate x.
Yes,
you cannot think of it as a inner derivative.
No, of course not. You're right. Essentially, exactly. So for the usual one are normal derivatives. Okay. For d thetas, okay, I use the fact that the interior derivative is a derivations. Okay, satisfy the Leibniz rule. Okay, and I use it algebraically. Okay, you're right.
Thank you.
If actually, if you look in the paper by Witten, he always stressed the fact that this is kind of an algebraic integration here. It is a kind of algebraic Berezin integral also for this object. So essentially, let's say I deduce the rules for this object from usual distributions. Okay, actually there is two ways. Either you start from an analytical property of distributions and you translate it in this language and you check it when this translation is correct. And it seems that it works. For example, even if you use the integral representation of distribution works perfectly, okay? And indeed with Carlo, we wrote a nice papers where actually we discuss how to do the calculations using these properties. However, there is another technique, if you like, Paolo, which is actually even more precise. And if you interpret those fields as conformal fields, okay, and then use the power of conformal field theory, then automatically using OPE, so short distance expansions of these operators, then automatically you get again the same rules, okay? So I have, let's say, two ways to check this, either using this analytical property of distribution, or using the geometrical properties which I derived from them, or using conformal field theory. Actually, I learned a lot of things doing string theory, where I use conformal field theory to do these OPEs. So, okay, there are some issues which are very, very tricky. I will like to mention some of them in a few seconds. Okay.
Can I make a short remark on this, like contraction iota alpha? I'm going to say something very naive,
Yes.
but which is in the end actually correct. So since you're actually looking at your d thetas as actual coordinates for a supermanifold, which is the supermanifold given by the basically the parity shifted total space of the tangent bundle, this iota alpha can really be seen as a derivation with respect to some coordinates, and these coordinates are actually the d thetas. So this iota alpha is really a derivation with respect to the d thetas. And if you look, for example, in the notes by Witten, he actually introduces this symbol derivation with respect to d thetas. So there's nothing too strange to speak about derivation with respect to d thetas. So this is really this guy over here, and this is really make this
yes, very good. Actually, using this, using this object, you can actually derive another rule, which is very important, which is the following rules.
No, but Simone, you confuse furtherly. I'm sorry about this. You confuse me furtherly because, sorry, if you look at, go back to the delta prime d theta, right?
Yes, this one.
Right. You're not doing contraction of an expression that contains d theta. You are doing contraction of an expression that for me is formal. So I don't understand what you're talking about. I really don't. What are you saying?
Integration by parts.
But yeah, exactly. As Paolo said, it's integration by parts. Right, exactly. Yeah, of course, let's say the n derivative of delta function is a formal object, but the way to understand this is, as Paolo says, integration by parts.
No, but that I was happy. Is Simone I don't understand.
What's the problem with thinking about the derivation with respect to the d thetas?
That usually I expect to derive something.
Is a coordinate.
Yeah, well, I expect to derive a function of d theta, but delta of d theta is not a function of d theta.
Well, it is a generalized function. I mean, a generalized function. I mean, it's not so strange object.
No, fine, but I'm like that. Is not clarifying remark, Simone. That's all I'm saying to me.
Okay.
Well, just forget it then. I don't know what to say.
No. Okay, fine. So they're not function. They're still generalized objects.
I'm just saying that basically, if you look at this construction as a construction over a manifold, which is canonically related. So the manifold I'm talking about is the total space of the tangent bundle.
Yes.
This contraction operator is really a derivative with respect to a coordinate.
Oh, I see. Okay.
This is all I'm saying.
But then it is applied to a strange function that is a form.
It is applied if you wish to a generalized function over your
Thank you.
well,
I see. I see.
So, I mean,
yeah,
an
really,
analog here is just how, like, taking the derivative of x to the n lowers the number of x's. That's
Exactly.
the contraction operator eliminates one of the d thetas.
that's
Yeah.
right.
Yes, thank you. John, you're always, thank you.
But, wait, okay, it doesn't eliminate the delta, okay? It eliminates the axis, if you like. It doesn't eliminate the delta. I will show you actually another operator which eliminated the deltas, but this is not, it doesn't not eliminate the delta.
I think John said that it eliminates the d theta that is in front of the contraction of the delta. Am I right, John?
Yeah, that's what I meant, yes.
Yeah.
Yeah, essentially, essentially, it says the following. For example, if I have a d theta, and then I have the contraction operators along delta. I fix now for me alpha now is fixed. Alpha is fixed, okay? Alpha is fixed. If I have this equation, okay, this equation means what? It is a d theta alpha. Then let me write down this as a derivative with respect to the d theta. Let's say I can also write down this way if you like, d theta alpha. Now I use again the distributional property, and then means integration by parts. So this is equal to -1, okay? Then this, let's say this derivative acts on the other side here, so I get the minus sign, and then it happens, this gives you a delta of d theta alpha, okay? So this property is very important, namely, every time I hit some derivative of delta functions of d theta alpha, I get a -1, and then I get, well, there is a number n here, and the delta of n-1 of d theta alpha, okay?
Okay, now it's clear, thank you.
Okay, now notice that once actually I hit by d thetas on this object, I decreases the number of derivatives. So this means the following: the derivative delta prime, or as I like to call it, a contraction along this d theta alpha, or the derivative of d theta, any kind of symbols you can use are the same, okay? But it is important to see that this object here, or this object, okay, they have -1 form number, okay? So since the contraction, it reduces the derivative with respect to theta, so it removes some d thetas, then it plays a role like a negative form number, okay? So this is very important because I can finally define an integral form p/m in the following way. There is, of course, the first term, it is the dx's up to the power of p and delta of d thetas, all of them, m of them, okay? But then I can also have another one, which is the following: dx's plus dx, not p, but p plus 1, and then I put a derivative, okay, one derivative, whatever, one derivative with respect to one coordinates, okay? And then I have delta of d thetas and delta of d thetas, okay? Since I have all of them, these derivatives will eventually hit one of them, okay? But notice that you have a p plus 1, and here I have a -1. So the total form number is again p. Of course, this is not the only one. I can also have another one. For example, I can increase this x to just to p plus 2. And then I put the two derivatives, for example. Two derivatives with respect to two variables, let's say 1 and 2 variables. And then I have the power, all the powers of deltas. Okay, and so on. Okay, of course you can go on, okay, and you can have up to this object, let me call it tilde, dx's up to the maximum number of x's. And then here I have to correspondingly put the number of derivative with some other coordinates, theta, I don't know, like some of them, I don't know, let me call it r, okay? Delta of
No,
d theta.
wait. I understand that the theta decreases by why you increase dx. I don't see why it
Well, because the total form number here, it is p, okay?
Yes.
So therefore, if I want to keep the same form number, so the form number is fixed, okay? So therefore, if I act with the derivative on the deltas, which means decreases the form number, in the same way, I have to increase the form number of the axis, okay? So you see, this object now is very nice. It's very complicated object, okay, because it contains several components, not just only one component, but several components.
So what I want to know is, why aren't those higher derivative terms 0?
Yeah, me too.
Right, when you integrate by parts, if you tried to integrate by parts to move that contraction onto the form, that form doesn't know how to.
Of course, no, yeah, I understand your question. Of course, certainly, this object, okay, this object now should act something. Okay, you have 2 points of view. Either this object in an integral, so therefore you multiply this object by some superforms, okay, and the superforms contain some data, okay, and therefore when you do the following, okay, so you have this object and p/m, you multiply by another form. Suppose that you multiply by a form like q0, okay. Of course, this object will depend on the data, okay, and then you integrate this object, okay, then you see immediately what happened to the derivative of delta functions. Then by integration by parts, the derivative of delta function hits this object, okay? And therefore, the higher terms in the superforms becomes important in the integral. That's one point of view. The other point of view is, look, now what I'm considering is an expanding a form in terms of Dirac delta function and derivative of Dirac delta function. And those objects now are my generators of my space, okay? And then what I want to show you now, how to manipulate this object. So namely, I don't have to think about them on which they act on, okay? I just only to use them as a symbol, okay?
No, fine. I have a question.
Is it clear, John?
Yeah, I think I understand what you're getting at.
Okay, very good. So there are 2 points of view. Either this object, you use it to integrate, namely is an integral form. Of course, if you take this object, you integrate those derivatives at 0. You're right. Okay. However, when you multiply by superforms, the superform will have some component along the theta which are heated, let's say, eaten by those, okay? And therefore, you remove those terms, okay? This is one point of view, namely integrals. But however, you can think about it as an integral form. So an object which is expanded on some fundamental generators. And the fundamental generators are derivative of delta functions. Okay.
No, I have a question that I don't understand, because you say that this omega has a picture number m, right?
Right, because the picture number counts the number of deltas.
Yeah, but you're contracting.
But the contraction of delta function, it doesn't change its nature. Namely, the derivative of delta function is still a distribution with the compact support. Of course, you have to act on the functions, okay? And then by integration by parts, you have to use these properties. But then still you put d theta is equal to 0, okay? So let's say the nature which says the atomic measure, we set the d theta is equal to 0 is still there, okay? So the contraction operator acting on Dirac delta function, it does remove the deltas.
Okay, go a little up.
Yes.
When you write a p+1 there, why can't you have a d theta there? Why?
Oh yes. Let's say you can. Why cannot put a d theta here?
Yes.
Very good. Okay. Yes, you can do it. Okay.
Okay.
You can do it. However, okay, it happens the following. Since here there is a contraction operator, and since this one you have to interpret it as an integration by parts,
yes,
then this means the following. Either this theta is along the derivative, then automatically by integration by parts, this object is removed. Okay. And
yeah,
therefore,
I take it along that. I take the same theta.
Okay, very good. If you take it along, it means by integration by parts, this derivative hits this theta here. And so then this means that you're just only rephrasing. So you're just reshuffling this component. Okay. On the other side, if d theta is not along the derivative, this means that the d theta is going to hit one of the delta function inside all of them. Okay. And then
then it's clear. Then is that 0.
Okay.
Yeah,
so
I still don't see why the omega prime, omega double prime, why is it in PM? I'm a bit disturbed. Why M doesn't change? That is what confuses me.
Oh, the M doesn't change because the number of Dirac delta function are always M. Oh, of course. Let me point, but this is just what I want to say. Maybe the next time, I suppose now. Okay.
Yes.
There are other complexes. Okay, and there are other complexes which has a number of delta function which is not M, but which is less than M. And those are what are known as the pseudo forms. And there you see the all glorious kind of murky stuff emerging. Okay, any kind of thing.
I'm not questioning. I don't want more general. I wanted to understand this one. Is a bit mysterious. Okay.
What is mysterious? I mean, Rita.
Yeah, why delta prime is one of the deltas, right? I don't see.
Delta prime, it is still a delta function. Okay, it's still a delta function which has a compare support equal to 0.
But you cannot express it in terms of the other deltas.
Of course not, but actually the way it works is that once you hit that with the function of d thetas, you integrate by parts, and then once you take the derivative, you put the d theta is equal to 0. That is essentially the point. So the picture tells you that you have delta functions or derivative of delta function is the same.
I see. Okay, no, now I see. Because M is the number of either delta function or derivative of delta function.
Exactly. Yeah.
Okay.
So let's say the contraction operator or derivative delta function, it does not change the number of deltas.
Okay.
Next time, next time I will show you that actually it exists an operator which actually it does remove the deltas. Okay, and this is called a picture changing operator. The picture changing operator indeed removes the delta functions.
Can I make a brief comment?
Yeah, sure, of course.
Confuse even more Rita's ideas, probably. So I'll try to be as confusing as I can. Actually, two remarks. So the first one is that you see that you have a finite amount of expression, of independent expression that you can actually write for a fixed degree and picture. Yes. So if you fix degree P and picture M, you see that you have, say a finite amount of, independent, let's say independent number of generators. So the first one is the first line, the second one is the second line, etc., etc. And I would like to stress that this stays true if you stays in the complex of integral form at any degree. And indeed,
absolutely, this is correct. Yes,
indeed, this is something very interesting because this is actually related to what I, what I tried to tell you last week. So this expression, degree by degree, arranges into a vector bundle or a sheaf, a locally free sheaf, if you actually prefer, which is nothing but the tensor product of the Berezinian with a certain symmetric product of the parity shift tangent bundle. So this is a different representation. Well, let's say a different representation you have if you basically think about your integral form as a section of a vector bundle or of a sheaf, leaving not on the, well, let's say, full total space of the tangent bundle, but only on the supermanifold.
Yeah. What actually Simone says is perfectly correct. Okay, and actually I would like to show you, I mean, how translate what Simone says in a handy way. Okay, I would like to do it, but now it's
yes, I'm sorry. I'm having another meeting at 5:30. I couldn't.
No, but I think that there will be a good moment to stop here. Okay. Next time I will show you first of all how to perform the differential on this object. Okay, which is important. Second things I would like to tell you, I mean, what actually Simone was saying in this framework. So maybe next time Simone will repeat the same sentence, and I will translate this sentence, I mean, verbatim. Okay, what actually said is correct, perfectly correct. I will show you verbatim what actually says using calculations. Okay, just only, okay. He says, I mean, they are section on a given, okay, I will show you that indeed they are.
Simone's statement was something global, was not something local.
Yeah.
No, okay, of course, I will show you locally, but then you'll see immediately that this object actually behaves as a tensors. Yes.
Yes.
So,
Yeah, this is actually, this is very important, Paolo. Only these integral forms behaves as a tensors. Yes.
Okay.
Yeah, but we will do an example of integration of supermanifolds, correct? The next time?
Of course, yes. Sure.
Yes.
Yeah, and about this, like regarding the comment made by John, I would say that, well, the part with the derivative, well, in some sense, you say that, well, you can see that this integral form of not top degree, you can tell that in some sense are related with integration on some submanifold of a certain bosonic codimension. So that's the point. And that integral down there is a sort of a Poincaré duality.
Yep.
Which, well, if you actually pick out the right section, I mean, if you do not pick out the right section, actually can give you 0 or can give you.
All right.
Whatsoever.
Okay, so guys, I'm sorry, but I have to go. So, but next time I was wondering if we can meet at 4:30 because I have another meeting. Is it okay 4:30 for everybody next time? Is a slight change again?
For me, it's okay. Yeah.
It's okay, but then I'll have to go at
5:30
sharply at 6, I guess. Yeah.
6. Okay, yeah, like me today. So
Okay.
all right, guys. So I say goodbye to everybody. Have a great and safe weekend.
Bye.
Thank you, Pietro.
Bye bye.
Ciao,
Thank
bye.
you, thank you, Antonio.
Ciao,
Thank you.
bye. Thanks.
Bye, everybody.
Ciao to everybody.
Ciao.
Right. So
I think you have to close it in such a way that.
yeah, I have to stop sharing. You have to stop sharing the screen.
Right, yeah, actually you have to do the termine. Scusa, basta che tu fai termina la sessione.
No, but I like to meet with my collaborator, Meng Kiat. He's here.
Okay. So
Antonio, meet Meng Kiat. Hi.
Ciao.
Hello.
He's my physicist friend I was telling you about, Meng Kiat.
Aha.
Right, yeah, so it's only the two of us. So as you can see, we're having meetings about integration on supermanifolds.
Yes. So first of all, I think this Zoom